Hello. In the last lecture, I introduced the binary distribution, and we are going to extend the binary distribution to the binomial distribution. So, as I promised last time, we are going to think of an interesting example, and we'll derive how we calculate the binomial distribution probabilities. So the example we considered in the last class was this. So think about reservations. There are 10 reservations you accepted for a flight, say, and suppose that the probability of cancellation is 10% each. For each reservation, they may be canceled, and the cancellation is independent across reservations. So two different reservations may be canceled, but they do not affect each other. And we denote cancellation as 1 and non-cancellation as 0, right? So cancellation is success and not cancel, non-cancellation is failure. This is just notation. It's just encoding. So I'm not saying cancellation is good. And then we are interested in the total number of cancellations in this situation. Then we say y, the random variable y, follows a binomial distribution with parameter n, comma p. In this example, the parameter values are given n. N is the number of experiments, repeated experiments. In this case, you are checking, the experiment is to check if a reservation is canceled or not. So choose a random reservation and see if it's canceled or not. And you are doing that for 10 times. So the first one reservation is one experiment, and you got 10 reservations. So there are 10 repetitions of the binary experiment. And in each experiment, the probability of success was assumed to be 10%. So P, the probability of success parameter, is 0.1. So in this case, I asked you, what is the probability that exactly 2 out of 10 reservations are canceled? You got 10 reservations. What is the probability that only 2, exactly 2, are canceled? So it's a very, it's an interesting question, and this kind of structure is very common in economics and in your daily life. So here, just guess. We are going to derive how to solve. I'll show you how to solve this question, and the answer. If try to guess it, actually the answer is the least likely, seemingly least likely answer. E is the answer. The correct answer is 19.37%. So usually there are, so the numbers you got are 10%, 2. So many students try to make up a number using those numbers given in the question, but the result is a totally different thing because there are some kind of complicated steps to go through to calculate this probability. So that's what I'm going to demonstrate today, and it can be a little bit difficult. So please follow carefully and listen carefully and repeat if you cannot follow. Like you may pause the video anytime, take a break and repeat. So I will spend quite a bit of time on this. Whole lecture will be about this. So our plan is I'm going to go through these steps to answer the question. First, I'll briefly review the concept of statistical independence. What's the properties and what we have if we assume independence. And then I will start from two reservation case. our question assumes 10 reservations, but let's start from 2. And then I will extend 2 from 3 to 4, and then we will generalize to any number of reservations. So 10 is just a special case of the general rule. So combination rule is a general rule of counting, so which will be very also useful. And then finally, we will get to the general binomial distribution probability. I will go through these steps. So first, let's review the statistical independence, the definition. So suppose that we have two events, A and B, or two random variables, A and B, both are binary, and if they are independent, what is not correct? So we assumed two random variables, binary random variables, are statistically independent, and then what is not correct? We learned it in chapter 2, in the chapter of about conditional probability. So think about it. I will turn the page in 3, 2, 1. So the answer is D. So let's think about this. When A and B are statistically independent, its meaning is they do not affect each other. So say probability of A equals to probability of A conditioned on given that B happened. Or similarly, probability of A also equals even if B does not happen. Or you may A and E, if you combine A and E, you obtain C. Probability of A does not change even if B is 0 or 1. So 0, B, the value of B does not matter on the probability of A. So A, C, E are basically the same thing, and B here is the special multiplication rule. Special rule of multiplication where the intersection, probability of intersection can be written as a multiplication of two simple probabilities. So probabilities are multiplied and you get probability of intersection. But D here, David, D has nothing to do with statistical independence. This is the special rule of addition, which holds if A and B are mutually exclusive, which has nothing to do with statistical independence. Mutual exclusiveness is defined such that two events have no intersection, or the probability of intersection is 0. So that has nothing to do with independence. So D does not make any sense. It does not hold even if A and B are statistically independent. So then you may use, so because in the binomial distribution definition assumptions, we already have statistical independence across n number of binary experiments. So we are going to use, particularly we are going to use B, beta. So this special rule of multiplication will be used later on. Keep that in mind. So we are going to use this. And this is the special rule of multiplication. And this holds in two cases, but we may extend the multiplication rule to multiple events as long as A, B, C are all statistically independent with each other. So A and B are statistically independent, B and C are independent, A and C are independent. Then you may write the intersection among A and B and C equals multiplication of every single probability, right? So this can be extended even to like larger numbers. So it's pretty intuitive. I would not prove it the idea, intuition is exactly the same. So anyhow, we are going to assume this. If there are 10 reservations, then the probability, if you multiply each probability, you will get their intersection probability. That's the first thing you have to understand, which is pretty straightforward as long as you remember the multiplication rule. And then let me ask you this question. Now we are going to think of two reservations case. So suppose that you only got two reservations. I will call the reservation names as A and B. So A and B made reservations. They are independent with each other, and each of them has cancellation probability 10%. In this case, can you think of this probability? This is really simple case. Then I calculate the probability that A is cancelled but B is not. See what is the probability. I am going to show you the answer in the next video. So try to answer this question. Hint is using the statistical independence, which is pretty obvious, right? So it's pretty simple, so you should be able to answer this question. I'm going to continue this in the next video.